Okay, welcome back, everybody. We're getting into perhaps the hardest section of the entire semester, at least from my perspective. The method of characteristics is super powerful, but because of that, you pay the price of having really difficult work in front of you. So it's like an inverse relationship between how powerful a tool is and how hard it is to use. So this is one of those tools that's really powerful, but can definitely be tricky sometimes. So we're just going to jump right in. This is the theorem. And this is the entire statement of the theorem takes up this much space, so that's why we can be a little bit terrified about what the theorem actually is saying. Let's jump into it. We have a first order PDE, and as I've mentioned before, the best way to think about a first order PDE is just as a function of my spatial variables, perhaps temporal variables, whatever my independent variables are, in their domain. The function also includes what I'm solving for. This is the scalar field I want to solve. And finally, we're looking at, since it's first order, the first order derivatives of the scalar field. And so the function f, we just think about, that's just a relationship between all three of those, maybe some constants as well. So we've got a relationship between all three of those and some constants. And we're going to set that relationship up against 0. We're just going to say that equals 0. And then we also always have a boundary condition, where if I look at the boundary of omega, we have prescribed the value of the solution along the boundary by some other function f. So f, we already know, it's given to us. It tells us exactly how phi looks on the boundary. And as I mentioned in the previous video, we're really trying to we're trying to use the information that we have from this PDE to trace out characteristics or trace out level sets so that we can extend the values from the boundary onto the interior of the domain. The way that we do that, the way that we manage to use the PDE to find characteristic curves, is we have to start by making a relabeling. So we take the x and we relabel it gamma. That's going to be our characteristic curve. Not really a surprise there that x is going to be gamma because gamma is flowing through the domain. We're going to relabel phi as a q, and we're going to relabel the gradient of phi as the vector, right? This is now a vector, p. Okay, so we're going to start by making that relabeling. I'm also going to relabel the element on the boundary as an x sub 0 or x naught. Okay, so what have I done? I've relabeled my original PDE now in the variables of gamma, q, and p, and I've relabeled the boundary as just some initial value on the boundary x naught. The whole idea is that we'll get really an initial value problem in the variables of gamma, q, and p prime, prime, along with the initial condition that gamma at time 0 has to be x0. Gamma has to start in the boundary. That's why we've given the indication in the boundary. So I'm going to make that relabeling, and then I'm going to construct a system of ODEs. Okay, so this is going to be a somewhat large system, unfortunately, for those of you who don't like systems of ODEs. You can't really perform the method of characteristics without it. So I'm going to construct a system of ODEs strictly out of f and then my new labels of gamma, q, and p. So gamma prime is going to be the gradient of f in the p variables, and it's going to gain the initial condition that it has to start in the boundary. Let's just rewrite that. That's always going to be in the boundary. So gamma starts in the boundary. Q, the time derivative of q, will be the variable p dot inner product with the gradient in the p variables of f. And finally, p prime, this is a vector valued ODE, p prime is going to be equal to, let's be careful about interpreting this correctly, this is the partial derivative in the q variable of f times, so that's a scalar, because f is scalar valued. So I've got a scalar times a vector here, and then I'm subtracting a derivative in the gamma variables of f. You could also think about this as the x variables because they're the same thing. Subtracting the gradient in those variables of f, and the gradient is going to reproduce a vector for me. So there's a vector, there's a vector, there's a vector, and this will be a scalar that multiplies my second vector. So what do I end up with? I end up with, this is a vector valued ODE, this is a vector value, or this is a scalar valued ODE, and then this is a vector valued ODE. So I'm going to mention this here, even in the lowest number of dimensions, non-trivial dimension, that would be R2, so two-dimensional. Two-dimensional is the simplest non-trivial case of a PDE. This is a system of, well, how many, that's a vector in 2 dimensions, that's a scalar, and that is a vector in 2 dimensions. So it's a system of 5 ODEs. So the simplest possible method of characteristics reduces a first order PDE in 2 dimensions, where the domain is 2-dimensional, into a system of 5 ODEs. That's the best we can hope for when it comes to the method of characteristics. So that's part of what makes this a difficult problem. Let's talk about the initial values here. So I already mentioned the initial value of every characteristic curve needs to be in the boundary. And we always just leave it as an arbitrary x0. We just say like, hey, that's a point in the boundary. We're just going to pretend like it's there as the initial condition. And then the initial condition in the variable q is always going to be, well, phi was q. And so it's just going to be whatever it is on the boundary, it's going to be evaluated at the boundary, which is going to be f of x. And then finally, p is the tricky one. This is where the initial conditions get quite tricky to think about. Everything would be really easy if I didn't have to think about the initial conditions in P. So what is this saying, the initial conditions in P? Well, this is the PDE, the first row is PDE is satisfied at the point on the boundary. Right, so at x0, whatever point that is on the boundary, the PDE itself needs to be satisfied. That is exactly the PDE. And secondarily, the second row, secondarily, recall what this gradient is. That's the gradient sub the boundary, meaning it's all the gradient which is formed from the tangential directions in the boundary. So secondarily, the gradient in the direction of the boundary, directions plural, must agree with those components of the vector p, right? Because the vector p is the gradient of phi, and I'm going to say, okay, so if the vector phi is the gradient of phi, what I can do is restrict the vector p to the boundary, and all that does is restrict my gradient to the boundary. And since I can compute the gradient of f within the boundary, I can compute the gradient of f within the boundary, because f is defined on the boundary, then certainly the gradient of phi, which is f on the boundary, needs to agree with the gradient of f on the boundary. So I'm gaining, my first row here is saying I'm satisfying the PDE within the boundary itself. This is saying I'm satisfying the boundary condition within the boundary itself. All very natural things to believe to be true, but of course that looks terrible, and sometimes it can play a terrible role in trying to make the method of characteristics start from the beginning. So we've got a system of ODEs that we're going to solve. At this point, we haven't solved our problem yet, right? We just have solved a collection of ODEs. And yet, after solving this collection of ODEs, if we look at this middle line, right, somehow, since Q is phi and phi is the solution, we should be able to find phi from Q. Now, in fact, you may be wondering, why isn't phi already Q? I should mention this in a separate row. Keep in mind that phi is a function of the variable x, but Q, here it is in an initial value problem functioning over time, is a function of the variable t. Okay, so somehow, so we must translate from the variable t, which parameterizes characteristics. So we have to translate from the variable t, which parameterizes characteristics, into the variable x, which is an element of the domain. So it's actually this extra step that sometimes make our life hard as well. I mean, these initial conditions made our lives hard, but it's this final extra step to say, all right, Q is technically our solution, but any given Q solving this system is technically a Q. It's a one-dimensional Q, right? Because it's been parameterized by T. Somehow I have to send Q back into a function of X. How am I going to pull that off? That's what step 3 is here. So in step 3, it says finding the gamma, right, which is just going to come from our system associated to something in the boundary, and the tau, which is some future time for which gamma tau equals x, right? Because if I can write that gamma tau is equal to x, if I know my characteristic curve at some time is eventually equal to x, then t is gamma inverse of x. Q of gamma inverse of x is going to be phi of x. So I can find phi by finding the very specific characteristic that I need to plug into Q. At this point, you can say that phi of x is Q of t. Let's actually get into some examples. I have a very nice proof here if you're into reading proofs. It's a little bit lengthy, so I won't go into it here. I do have a brief remark on this where I say, ironically, we don't test for the non-characteristic condition when we actually apply the method of characteristics. The primary reason for this is that you end up failing if your non-characteristic condition fails. So I could just start running the method of characteristics, and if I get to a point where I've failed to complete anything, then it means that my non-characteristic condition failed. So that's just something to keep in mind. I often avoid testing for the non-characteristic condition, even though we probably should do it. You can save yourself some effort from the beginning if you want to test for it, but it's totally up to you. Let's get into some examples. So this first example is a fairly straightforward one. I've got the variables t and x, and I'm looking at the first order PDE x partial t plus t partial x equals phi. And I have some initial conditions x times x minus 1 along the entire real line. So the first thing I need to do in every single round of the method of characteristics, if I jump all the way back to my theorem, is step 1, relabeling the variables. Right? I'm going to relabel my vector x. So keep in mind that could have a t inside of it, the vector x. I'm going to relabel that gamma. I'm going to relabel phi q, and I'm going to relabel the first partial derivatives as p's. So jumping back down to the example here, what's going on? This is going to be called gamma 2. This is going to be called gamma 1. This is going to be p1. This is going to be p2, and that's going to be q. And this is because I'm making the choice that gamma 1 should be associated to the variable t, gamma 2 should be associated to the variable x, p1 then is partial in time, p2 is partial in space, and finally q will always just be phi. So that's where all of those are going to come from. And then I'm also going to remark that my boundary, instead of being an x, will be an x naught. And then we should be good to go, because all I need to do is establish what is the function here. Well, the function f of gamma 1, gamma 2, q, p1, and p2, if that's equal to 0, I need to bring the q on the right-hand side to the left-hand side. My function is going to be gamma 2, p1 plus gamma 1, p2 minus q. So this is going to be my function f. At that point, I can set up my system. So let's jump down. There's the function f I just found, and I'm going to set up my system. Recall my system is here. This should be the gradient in the p variables of f. What's the gradient in the p variables of that? Well, the gradient in the partial in p1 is going to be gamma 2, partial in p2 is going to be gamma 1, and the q is not going to show up at all. So that's why that's gamma 2, gamma 1. Q, you'll recall, will always be p as a vector dot product the gradient in p of f. Well, I just calculated the gradient in p of f. That was gamma 2, gamma 1. If I dot product that against p1, p2, what does the dot product give me? It gives me p1, gamma 2 plus p2, gamma 1. So there we go, p1, gamma 2 plus p2, gamma 1. Finally, the last step will be p prime. What does p prime look like? It always looks like negative partial q f times p, the vector, minus the gradient in gamma of f. So let's find partial q of f. If I take partial q, I'm getting negative 1. Let's multiply that against p. I end up with negative 1 times p1, p2, minus what is the gradient of f in the gamma variables? The gradient of f in the gamma variables is p2 is the partial derivative in gamma 1, and then p1 is the partial derivative in gamma 2. So p2, p1. If I add all those correctly together, I end up with exactly what I have here. Okay, so this is going to be our system of ODEs. And then we are going to figure out what the initial conditions should be. So to figure out the initial conditions, let's recall. gamma as a vector at time 0 always needs to be on the boundary. Okay, this is the number one thing we have to say about gamma. It's an arbitrary element of the boundary. Let's recall what our boundary actually looks like. There's our boundary. On the boundary, time is always 0. So if gamma, which is gamma 1, gamma 2, and I already had made the decision I was going to do time and space, then if I'm on the boundary in time, time has to be 0 on the boundary. And then I need an arbitrary element in space. That's going to be x sub 0. So that's going to have to be my initial condition is 0, comma, x sub 0. That's why I have this initial condition. For gamma, if I want my initial condition in Q, let's go back up. Recall that Q and phi are the same thing. So that's Q. And I'm just going to exactly extract this, except I'm going to recall that I'm using an x sub 0 for my initial condition. So I'm exactly extracting that for Q at time 0. Scroll that down. Q at time 0 has to be x naught times x naught minus 1. Finally, P at time 0 is the tricky one, right? All of these, where the heck did these come from? Let's figure out where those came from. Recall, there are two things that happen, two parts for the initial condition on P. We have that the PDE is satisfied on boundary, and we have that the gradient on the boundary of Q, which is the same as F, the initial condition, but I'll just say Q. Gradient on the boundary of Q happens to be P restricted to the boundary, because P by definition has to be the gradient of Q. So let's figure out what those two things would mean in this situation. The PDE being satisfied on the boundary. Recall our PDE, or a function F, of gamma 1, gamma 2, Q, P1, and P2 equals 0. That function was gamma 1, P2 plus gamma 2, P1 minus Q equals 0. And we're gonna emphasize that this is all occurring on the boundary. Where's the boundary? It's right here. Gamma 1 is 0, gamma 2 is x0. So gamma 1 is 0, gamma 2 is x0. Moreover, Q on the boundary is right there. Q has to be x0 times x0 minus 1. And so now that I've plugged all those values in to my PDE, what do I get? Well, there's a 0 term that doesn't show up. I get x0 P1 minus x0 times x0 minus 1 equals 0. So that's where this line comes from. It comes from me just plugging these into the PDE and seeing what shows up. And then where does the second line come from? This has to come from me calculating that P restricted to the boundary, the vector, equals the gradient restricted to the boundary of Q. Well, there's Q. What do you suppose the gradient restricted to the boundary is? Let's figure out what the boundary looks like. Jumping back up here, the boundary looks like this, which is just t equals 0 permanently, and then I have my real line here. So what is the tangent direction to that real line? Well, it's just literally that direction. The tangent direction to a line is the line itself. So this is the direction I'm computing a derivative in. That is just the direction partial x, because it aligns with the x-axis. So jumping back down here, Q partial, well, I'll call it nabla of the boundary on Q has to just be the vector partial in the direction of the boundary, which is just x, of x naught minus 1. If I take a derivative of that, what do I get? I get 2x naught minus 1. That has to be P restricted to the boundary, but the boundary is just the x-axis, so it's just the x component of P. You'll see that that's the t component, that's the x component, it's just the second entry of P has to exactly be 2x naught minus 1. So that's where those numbers came from. And now that we've set up our system, we can solve our system. And in fact, the system's not too bad to solve. What are we going to do to solve it? The first thing I'm going to do is solve my system in gamma, because it only cares about itself. No, thankfully, in this situation, gamma only cares about itself, so I can solve the system in gamma. Similarly, the system in P only cares about itself. This isn't always true, by the way, but in this case, these systems are distinct, where gamma only cares about itself, P only cares about itself. So I can solve those two systems independently. And then Q, the derivative of Q is only a function of P and gamma, so once I find P and gamma, all I have to do is integrate them to find Q. So I'm going to do just that. And we're going to solve this system in gamma first. Jumping back to section 1, hopefully everybody feels good about systems of ODEs now. I can solve that system for gamma 1 and gamma 2, I get x naught sinh s and x naught cosh s. I'm using the variable s because t already showed up in my PDE. So I'll mention that here, use the variable s because t was in the PDE, and I just would rather not accidentally use 2 rounds of t. So let's use an s here, and that's me solving my system in gamma. I can also go ahead and solve my system in p. Solving the system in p isn't too hard either. It's just another matrix exponential, and we end up with p1 being negative e to the negative s sinh s on x naught plus x naught minus 1, and then p2 is e to the negative s cosh s times x naught plus x naught minus 1. And these, of course, extra terms are coming out of us needing to satisfy those initial conditions, so we have to choose our constants of integration wisely or go through Duhamel's formula, etc., etc. So now I've found all of the gammas in terms of only the initial condition in s, initial condition s, same with the p's, initial condition in s, initial condition in s. If I jump up to what is my function in q, q prime is p1 times gamma 2 plus p2 times gamma 1. So if I scroll down here, I'm just going to remember that p1, I just found it, gamma 2, I just found it, p2, I just found it, and gamma 1, I just found it. So I'm just plugging all of those in, keeping the initial condition in mind. And when I do that and simplify, this actually simplifies very nicely, this collection of p's and gammas, simplifies very nicely just to negative x times x minus 1 of e to the s. And then I have my initial condition that needs to be satisfied as well. So it turns out very, very easily that you just integrate this and you exactly get rid of a negative sign when you integrate it and find the correct constant of integration. So we end up with that q is x naught minus 1 e to the s. So to finish this, we're going to note something, right? Because this is our solution. I'm putting that in quotes. It's only the solution along the specific characteristic curve that starts at x naught in the boundary. Okay, so it only starts at that one specific x naught in the boundary. We want this characteristic curve to extend all the way through, and ideally we don't actually want this dependence on s. We don't want dependence on the boundary either. We want dependence on x, which is inside of omega, and t, which is inside of omega. We don't want the dependence on x naught, which is on the boundary, and s, which is some parameter. So what do we have to do to rewrite q in terms of, I guess that's what I'm tending towards, is how do we rewrite q in terms of x and t rather than x naught and s? And we start with gamma. Gamma is what's going to give us the ability to make this happen. So what do? We start with gamma, and we say, hey, I want gamma to actually be written as t and x. I don't want it to be written as x naught and s. X naught and s. I want it to be t and x. So what I do is I have a system of 2 equations and 2 unknowns and solve for x naught and s. So notice here x naught and s are not solved for, t and x are solved for. So I'm going to solve this for x naught and s. And in the process of doing that, let's just write it out as 2 horizontal lines. I'm just reading across here. What should I do? I'm just going to use the method of substitution, which means I'm going to solve this for x naught. And to solve for x naught, I just divide by sinh. Easy enough. X naught's t divided by sinh. I then substitute that t divided by sinh in for x naught in the second equation. So if I grab t over sinh and plug it in for x naught, I get t tanh s equals x. Then if I solve for s here, I get s is tanh inverse x over t. Okay, so that's not too bad. You can actually search for other forms of tanh inverse and find out that it's actually equivalently log of root x plus t over root x minus t. So you can write s in either of those 2 cases. You then have found s in terms of x plus t. How can I find x naught in terms of x and t? All I do is I plug this s into the x naught version, and I go through some simplification with hyperbolic trigonometric identities, we find out that x naught is actually root x squared minus t squared. So what have I just found? Let's make sure we know what we just did at this very last stage. I've solved for s and I've solved for x naught in terms of the variables x and t. What I do with this is I plug, note, q of s is really a function of x naught and s, because q emanates from the boundary. Okay, so q emanates from the boundary, which means that it's really a function of x naught and s, and I've just found a way to write x naught in terms of x and t. So that's in terms of x and t. I've just found a way to write s in terms of x and t. So that's in terms of x and t. And so what I can do to finish this off is rewrite phi of t and x is actually q of x naught, but x naught is here, root x squared minus t squared. And what is s? S is right here, and log root x plus t over root x minus t. So I take those two terms for x naught and s, I find q, which we have right here, and I plug x naught, which we just decided was root x squared minus t squared, as well as s, which is log root x plus t over root x minus t, into here. And when I plug those into there, what I end up with after some simplification is x plus t times root x squared minus t squared minus 1. So now I have a function of only the variables t and x, which completely was constructed out of this system of equations. That is the method of characteristics. And in fact, I'm going to stop there today. We have 2 more examples, and we're going to get through these 2 other examples, but they really do take a long time, and we have to be careful about all of this. This is not an easy thing to do. Ideally, you've probably noticed that by now. But take your time, work through this example, and ask me in class if you have any questions. Anyway, that's all I've got for you. I'll see you later. Bye.